All right. Okay. All right. So what we were talking about on Friday was looking at quantum mechanics, the very basics of quantum mechanics. And we were looking at how we can find electrons around an atom. So we started talking about the principal quantum energy number, n, which is just energy level. The smaller the value of n, your lower the value of your energy, and the closer you are to the nucleus. Angular momentum quantum number, which we call L, is the shape of probability, or the probability shape of finding your electron around the nucleus. So if you're an electron and you're in an s orbital, you're going to be found in a sphere, somewhere in that sphere around the nucleus. If you're L equals 1, you're a p orbital, which is those two balloons. L equals 2 is d orbital, and L equals 3, f orbital. Then we have this m sub L, which is basically what does your orbital look like. For the p orbital, we have 3 different orientations. So you can be on the x-axis, the y-axis, or the z-axis, right? And so our 2 problems were we looked at just orbitals, and we also looked at L and m sub L. So we did question 1 and 2. So let's continue on to 3. So what do all these numbers like mean? What are these n, l's, m sub L? What can they tell us? Well, like I've said to begin with, these tell us where to find electrons. And what we're seeing here is an energy level diagram. So let's just look at this image piece by piece and see what's going on. So at the very bottom here, we have n equals 1. That's our first energy level, all right? And for the first energy level, we only have one angular momentum, 0. Remember, L goes from 0 to n minus 1, right? And if we have L equals 0, then we only have one m sub L, which is 0. Remember, m sub L goes from negative L, 0 to plus L, right? And so we draw a box. Every time we have an m sub L value, we draw a box. And what this box tells you is how many electrons are in that orbital. So in each box, and I'm going to just redraw the box out here. So for each box, you can have 2 electrons. 1 electron's pointing up, 1 electron's pointing down. That's actually another quantum number we call the spin. And spin can only have 2 values. Plus 1/2, minus 1/2. Just basically means an electron's pointing up or electron's pointing down, which just means for every box we have 2 electrons, right? So we go to the n equals 2 level. Now we have 2 L values, 0 and 1. In the 2s orbital, we can have 2 electrons. In the 2p orbital, we can have 1, 2, 3, 6 electrons, because there's 3 boxes, and those 3 boxes come from our m sub L values. So when L is 1, m sub L is minus 1, 0, and plus 1. So in total, we can have 8 electrons at the second energy level, 2 in the 2s orbital, 6 in the 2p orbital. And let me just mention, I'm not sure if I mentioned the naming system before. So the naming system is what energy level you're at, followed by what angular momentum you're at. So that's why you're seeing 2s, 2p, because you're at second energy level, L equals 0, 2s. Second energy level, L equals 1, 2p. Then we can do this forever if we wanted to. So the last example here is n equals 3. We have 3 L values. And with 3 L values, we get 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. Every box gets 2 electrons. So at the third energy level, we can fit 18 electrons. So in general, what I have over here, your energy is N. The number of orbitals is going to be 2L plus 1. So what that means is if we look at the L plus 1, it's 2 times 1 plus 1, which is 3. So this is how many boxes for each L. And the number of orbitals in total is another way you can do that is n squared. So if n equals 1, 1 squared is 1. So you only get 1 box. And every time you see orbital, that's these boxes. So these orbitals are boxes. Yeah. N equals 2. 2 squared, which is 4. So we have 4 boxes. N equals 3. 3 squared, which is 9 boxes. So there are mathematical ways to do this as well. But again, all we're doing here, I know this is probably super confusing to go through. All we're doing here is just asking ourselves at these different quantum numbers, how many electrons are there? That's all we're asking. We're just figuring out how many electrons and where can we find these electrons. I'm going to skip probability distributions just because for the sake of time. So we can skip these. What I just said previously was probably confusing enough that I don't have to get into probability distributions right now. So yeah, we're going to skip probability distributions. All right. So here's some questions to test our understanding. And I have polls for all these, for most of these questions, if not all of them. So let me get the poll up and let's see how well we understand the information from Friday and Monday. And if we don't understand it too well, that's okay. I can go over it again. So see how you handle these questions. So take a minute to try and answer those. do about another 45 or so seconds. See if you can answer these. All right, so let's take a look. So which orbital on average is closer, 2s or 3s? As most of you got it, it was the 2s. Basically, the smaller the value of n, so smaller n, the closer you are to nucleus. It doesn't always work out that way. There are a lot of discrepancies for that. For example, a 4s is going to be closer than like a 3D. But if you're looking at 2s versus 3s, the 2 is always going to be closer than a 3. So if they have the same L value, you can just tell by the N value which one's closer. And in general, the lower the number, kind of the closer it is. All right, what set of quantum numbers cannot specify an orbital? That is C. Because remember, our rule is that L can only go to 0 to n minus 1. So if n is 3, L can be 0, 1, or 2. L can't be 3. That breaks the rule of our values of L. L can only be 0 to n minus 1. Okay, so of the real orbitals in question 2, which is closest, which is farthest, so that would be A is closest, n equals 2. Farthest would be D, n equals 4. Okay, which of the following of n and L represent real orbitals? Which ones do not exist? So real. So this, let me pull up the poll again, because this one was all over the board. Yeah, yeah. So I'm just going to remind you what these letters mean. S is L equals 0. P is L equals 1. D is L equals 2. So when I say 1s, I'm saying n equals 1, L equals 0. Yeah, that's real. 2p, n equals 2, L equals 1. Yeah, that does not break our rule, so that's real. 4s, n equals 4, L equals 0. Yeah, that does not break our rules, real. 2d, n equals 2, L equals 2. That breaks our rule, right? L can only go to 0 to n minus 1. 2D is saying energy level 2, L equals 2. Not possible. So D is fake. Questions about the information presented here, or now that you had a little bit of time to think about it, any questions about our quantum numbers? For D, can you just look at the periodic table? If you know how to read the periodic table to get quantum numbers, you can. The periodic tables I provide on the test don't have that. But yeah, you can, if you know how to read it to get that information, which I'll cover in a week or so. But yeah, you can definitely do that. All right. So now our next question here. For energy levels, I showed you how to figure out the number of electrons for energy level 1, 2, and 3. How many electrons can have an energy level of 4 then? Try and figure out that information. I'll give people a minute or two to see if you can figure out how many electrons for n equals 4. So yes, it is actually 4 raised to the power 2, I believe. 4 times 4. Well, that's not 32, is it? 4 squared is 4 times 4. 4, 8, 12, 16. But the correct answer, yeah, it's the correct answer should be 32. I'll show you the long way to do it. So n equals 4. Because I actually don't remember the math of like how to do it, but I know how to do it by looking at the orbitals. So if n equals 4, you have 3 values of L. You have L equals 0, L equals 1, L equals 2, L equals 3. So I'm just going to add on to this n equals 3 and just make it n equals 4. And just make another box. L equals 4. Well, or sorry, L equals 3. If L is 3, then m's of L could be -3, -2, -1, 0, 1, 2, 3. Every time I make an m's of L, I draw a box. 1, 2, 3, 4, 5, 6, 7 boxes, right? And for every box, I get a 2 electrons. So if I have 7 boxes, that's 14 electrons. L equals 2 has 10 electrons. L equals 1 has 6, 2. So in total, so 10, 14, that's 24 plus 6, 30 plus 2, 32 electrons. So at n equals 4, we can have 32 electrons. And let me just go back to the math on that. So to figure out the math, it's n squared for the number of orbitals. And then you multiply that by 2. So it should be 32. Let me redo my, there we go. Any questions about finding the number of electrons in an energy level? So it should just be n squared times 2 for number of electrons. Right. Okay, so the last thing we're going to talk about is calculating these atomic spectra now. So we already kind of talked about this for the Bohr model, and the Bohr model has a good, basically approximation of what's going on. But the reason why elements absorb light is that we are taking an electron from one orbital to another orbital at a higher energy. The reason why elements will release light is that that electron is going back down to a lower energy. For example, if I have an electron at 2s and I hit it with light, it could be promoted to like the 4s orbital. Then at the 4s orbital, if it comes back down, it will emit light. Basically, if you want to go to a higher energy level, you need to absorb light. If you want to go down to a lower energy level, you emit that same light. That's why neon, when we hit it with electricity, it will relax and let off that light that we see in neon lamps. And of course, we have an equation for this. To know what energy of light that is released, we have this equation where we already looked at this one. Planck's constant, which is h, so that's Planck, times the speed of light, divided by wavelength of light. That will give you the energy of one photon of light. Well, we can calculate the energy of a photon if we know what energy levels we're moving to and from. So the energy of a photon is also equal to 2.18 times 10 to the minus 18th joules. Remember, energy has unit of joules, multiplied by 1 divided by our final energy level, so just our n, minus 1 divided by our initial energy level. So that will give us light. So this will hopefully become more clear when we do an actual problem. So I will do A. But here in question 5, all I'm asking you is to calculate wavelengths of light, and I'll do A for us. Okay. So the equation we want to use is on the bottom, right here. Right. So in A, I'm going from 4. So 4 is my initial. 3 is my final. So I'm going to plug that in to just calculate the energy of a photon. So E photon equals 2.18 times 10 to the minus 18 multiplied by 1 minus final squared. My final is 3 squared, minus 1 divided by initial energy level squared, which is 4. So when I do that, I find out the energy of a photon for this transition is 1.059 times 10 to the minus 19 joules. So that's one part. Part 1 is what is the energy. However, if we actually read the question, I'm saying, what's the wavelength? So that is the other half of the equation, right? Remember, wavelength is this Greek character right here. So I just found the energy of a photon, and now I want to calculate wavelength. So what I'm going to do is I'm going to rearrange my equation down here to solve for wavelength instead. So instead of hc divided by lambda equals E photon, you can have hc divided by E photon equals lambda. All I did was switch the location of those two variables. And you can do that if you're careful, right? If you're good at algebra, you can definitely do that. Because all I did, just so you know, is I multiplied lambda by each side of the equation, and then I divided each side of the equation by E photon to get my new equation here. And then solve for lambda. So energy of a so Planck's constant is a constant, 6.626 times 10 to the minus 34. Multiplied by speed of light, 3.0 times 10 to the 8. I'm just simplifying our speed of light right here. Divided by energy, 1.059 times 10 to the minus 19. Our wavelength of light is 1.876 times 10 to the minus 6 meters. The last thing I'm asking you is, where is this found? So we look at our electromagnetic spectrum. And here, visible light is 4 times 10 to the minus 6 to 7.5 times 10 to the minus 6. So our actual wavelength is below, to the right of violet. And if we look on our spectrum, to the right of violet is ultraviolet. So this is UV light with a wavelength of 1.876 times 10 to the minus 6. All right. So again, I'm sure that looked like quite a complicated calculation I did there. But it's really just plug in the variables that were given and then rearrange to solve for wavelength. But and then reading our chart. But is there any questions about any part I did about that equation? Where did I lose folks on? What were you confused of what I did, why? Anything like that. So I'm not sure what's happening, but I plug the equation in the calculator, but I'm not getting the same number. If you plug that whole thing in the calculator and you're not careful with your parentheses, it will do an order of operations that you're you weren't thinking of doing, right? So the way I actually do this in my calculator is I do 1 divided by 9 minus 1 divided by 16. I do that first and hit enter, and then multiply by 2.18 times 10 to the minus 18. That's how I do it piecewise. E photon and initial, where you have 1 divided by 3 raised to the power of 2. So right, the second part, the parentheses, is final minus initial. The 3 is where we're going to. That's where the arrow is saying, where our energy level final is 3. So that's why it's 3 squared. And our initial was 4 on the left-hand side. So it's saying we're going from 4 to 3. That gives us our final and our initial energies, our energy levels. So that's why it's 1 divided by 3 squared, or 9, minus 1 divided by 4 squared, or 16. All right. So what we're going to do is I showed you how to do this calculation. I'll put the answers up. But since this calculation isn't actually on the test Wednesday and we have 20 minutes left, I will reserve this next 20 minutes for you to ask anything that you want about the test. If you want me to redo some question from some PowerPoint or some question from some homework, feel free to ask me. I'll get the regular ones out of the way. 17 questions. About 7 let me see how many. About 8 or so, I want to say 7, 8, 9, something like that, are multiple choice. You have one little mini essay, one problem where you have to do words, and the rest are calculations, right? So the multiple choice, generally you don't have to do calculations for. There's one thing where I ask you to describe something that's happening to me without doing calculations. The rest are calculations. So that's how the test is laid out. I did it this morning, and the test took me approximately 6 to 7 minutes without looking at an equation sheet. So I was remembering the equation from my head. I will give you an equation sheet. I don't think I posted that yet, but I will post it. And as always, the test will be open from 12 a.m. to 12 p.m. on Wednesday. All right, so that's the general stuff for the test out of the way. Anyone have specific questions? I can stop sharing this. We don't need to be looking at it. Look at my wonderful face instead. Questions, concerns, complaints. Now it's your time to ask anything that you want. Any problem you want me to redo. You can ask me anything except show you the test. I will not do that. I'll do just about anything else. You got a haircut? Yeah. I was getting sick of hair touching my eyes. So I had my wife do that. So for the equation for the laws, it will be given any equation that we went over in class. I put on the equation sheet for you. How many multiple choice? Like 7 to 9, something like that. And some of the multiple choice are like true and false. So like, hopefully those will not take long to think about. Speak now or forever something something. Hold your peace. I mean, we can also just leave early if you want. If you don't have any questions for me. Your internet cut out? Well, you haven't missed anything. People have a good Halloween. Tasty candy. I had some, so we laid a candy bowl out, and we have a camera in front of the house. And you just see a couple kids just come over and like scoop, 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 and leave like 5 pieces out of original 100 for the rest of the kids. Come on. If I think of any questions later, can we email you? You sure can. Can we go over molecular velocity? Sure. Should we study the example problems? Yes. Study the example problems. Study my previous tests. You should do fine. Molecular velocity. Which date was that? Partial pressures, kinetic molecular theory. So it should be, all right, kinetic molecular, yeah, sure, molecular velocity. Let me share that. So molecular velocity is this equation here. So the whole idea from this is that gases have the same kinetic energy based on their temperature, right? So no matter what gas you are, you'll have the same average kinetic energy as any other gas as long as you're the same temperature. However, kinetic energy is different than velocity. Velocity is how fast something is moving. Kinetic energy is just how much energy you have. So velocity does change based on your mass. So the heavier you are, the slower you go. The lighter you are, the faster that you go. And our molecular velocity equation is here. So this U, RMS, means molecular velocity, equals 3 times RT divided by molecular mass. So what is here I have Cl2. I think the molar mass of Cl2 is like 90 something, because I think Cl is like 45.45. So if I do this, my molecular velocity equals the square root of 3 times our gas constant. So for molecular velocity, you need to use the gas constant that's joules per mole K. The reason is when we do this, our unit is going to be meters per second, because that's the velocity, right? It's movement per speed, right? And the only way to get meters per second is to be in joules. So we have 3 times our gas constant times what temperature we're at. So our gas constant is Kelvin. So our temperature also needs to be in Kelvin. So we're at 25 C. To make that into Kelvin, we add 273 to it. This is 298 times 298 divided by my molar mass in, so for this, our molar mass needs to be in kilograms per mole. So that's another caveat to our molecular velocity equation. This needs to be kilograms per mole, which we've never used before up to this point. The reason why is if we look at what a joule is equal to, 1 joule is kilograms meter squared seconds squared. So we need to cancel out the kilojoules. So instead of 90, you're going to put in 0.09, because 90 grams, there are 1,000 grams in 1 kilogram. That's 0.09. You solve for that, you get a speed of meters per second. That is molecular velocity. Do some questions have parts like the last exam? I don't think so, no. Yeah, I don't think I have a question that's part A, B, C, and D this time. Yeah, no, because I just took it. I took it like at 9:50, like right before class. And I don't remember A, B, and C, and D. Yeah, I don't think so. Partial pressure, can I do an example? Sure. Let me get that slide up. There it is. So the idea of partial pressure is that when you have a gas mixture, the pressure of that mixture is additive. And really, partial pressure is just, what is the pressure of this one individual gas? And there are different ways to go about that. So one way to go about that, well, here is one way, right? So this equation, PV equals nRT, is our ideal gas law, right? And so if we know the partial pressure of a gas, so let's say we have a mixture of N2, the pressure is like 0.25 atmospheres. O2, let's say 0.10 atmospheres. Argon is 0.70 atmospheres. And carbon dioxide is 0.20 atmospheres. Just made up numbers, right? we can figure out how many moles there are of these gas by doing PV equals nRT and just using the pressure of the gases themselves. So you just plug in, for example, N2, and that will tell you how many moles of a gas there is. Total pressure of this gas, you just add up everything together. And I'll tell you the total pressure of this gas. Let me see what I have on the next page, because partial pressure is really not more complicated than that, right? So here I do have an example where I'm asking you, what's the total pressure? Add it up. What's the mole fraction? So mole fraction is just mole of example N2 divided by your total moles. And that'll give you a mole fraction. That is, what fraction of my moles are made out of N2 gas? What fraction is made out of O2 gas? And then what mass of gas is present? That's just molecular weight, right? So if I have 1 mole of N2, the molar mass of N2 is what, like 14 or 28 rather? That's 28 grams. Yeah, so that's partial pressure. Nothing more complicated than that. It's just all gases when added together, and you want to know the pressure of that mixture, all the pressures are additive. Another way I could ask this is I give you moles of a gas and ask you what's the total pressure. And basically, anytime for this test, if you see gas, there's a good chance, a very good chance, you want to use PP equals nRT. Anything else? So I guess that's my pro tip for test 3. You see the word gas, I would be thinking that. Can I go over the slide on October 23, where we talked about the first relationship, second relationship? Yeah, I can probably do that. Let me answer this one. If we start with moles, how would we find pressure again? You rearrange PV equals nRT, number of moles equals PV divided by RT. Or if you just want to get pressure, you just get P by itself. So pressure equals nRT divided by V. So if I give you moles, I would also have to give you volume and temperature to get pressure, but you could do that. Okay, October 23rd, where we go over first relationship, second relationship. So let me do that. Where? Oh, there it is, October 23rd. Oh, okay. Yeah, enthalpy stuff. When will you put out the formula sheet? I'll put that out today. Okay, so this is Hess's law to tell us how delta H changes based on how we manipulate questions. And this was like one of the things we had on our homework to give us practice for this. Delta H is extensive. That means if we double the amount of stuff in our reaction, we double delta H. So for example, if we're looking at equation 1 and equation 2, the only difference between equation 1 and equation 2 is that I multiplied everything by 2. So instead of C, I have 2C, O2, 2O2, CO2, 2CO2. So to calculate delta H, you multiply your original delta H by 2. In our example problem here, I have A plus 1/2 B goes to C is X. So if I have this second equation, which is the same as the first equation, second equation, except everything's doubled, delta H is 2x. So that's our first relationship. If I multiply my equation by something, my delta H has to be multiplied by that. if I divide by something or multiply by a fraction, I have to do the same thing. So anything you do to your equation, you do that to delta H too. And the second relationship is if you reverse an equation, the sign of delta H is changed. So here we have carbon plus oxygen goes to CO2, negative number. If I just flip the equation where CO2 is now going to carbon plus oxygen, that negative becomes a positive. I just change the signs when I flip the equation. So our example problem here is we're using both the second and the first relationships together. So equation 1, I have A goes to B plus 2C. In equation 2, I have 1/2 B plus C goes to 1/2 A. So the first thing I've done here is I reversed the equation. So the equation was flipped to now be B plus 2C goes to A. So delta H of that would be negative X. But it was also multiplied by 1/2 to get this. So my final delta H is negative 1/2 X. That's the first and second relationship. Hess's law. Got time for one last question. Mo ichido ite kudasai. One more question. Well, if there are no questions, do we have one more? Can I go over an example problem with the second relationship? Sure. That would be A to B. If A is A plus 2P goes to C plus 3D, what's C plus 3D goes to A plus 2B? Negative 155. I flip the equation, I flip the sign. And now I can do the other ones. Here, I just multiplied everything by 3. So delta H is multiplied by 3. C, I flipped it and multiplied it by 1/2. So it's negative 155 multiplied by 1/2, whatever that is. Can I do the hard one? What's the hard one? I can give you another example if you want. A plus B goes to C, delta H is 1 million. So then what is 10C goes to 10A plus 10B. So I flipped it and multiplied it by 10. So that would be negative 10 million now. That's all. Anything I do to the equation, do it to delta H. Not sure what the hard one is. I think all of these are easy myself, so I'm not sure either. And I would hope I would think they're easy after doing it for a while. This maybe. I can do this one since we're on here. Calculate delta H. So this not only uses the first two relationships, but you have to put them together like a puzzle to make my target. So this is my target. These are my pieces. I need to make these look like that. So the first thing I'm going to do is I look at iron 2 oxide and see that, oh, it's my target is a reactant and my pieces is the product. So I need to flip that if I want to make my target equation. So Fe2O3 goes to 2 Fe plus 3/2 O2. I flip the equation, so delta H also becomes flipped. And if I see on my equation, I have 3 CO. Here I only have 1 CO, so I need to multiply everything by 3. So 3 CO plus 3 half O2 goes to 3 CO2. I multiplied this equation by 3, so delta H for this needs to be multiplied by 3 as well, whatever that is. And then I can add these together. When I add them together, I get Fe2O3 plus 3CO. Anything that's a reactant stays on the reactants. Anything that's a product will become a product. Let's see, I messed something up. Plus Fe2 goes to, I misdrew my arrow. Yeah, that's a plus right there. All right, and when doing this, if something is on each side of the arrow, right, I have 3 O2 on the left side, 3 O2 on the right side. If they're on opposite sides of the arrow, they will cancel out, right? So it's basically like having 3 O2 minus 3 O2. That equals 0 O2. So Fe2O3 plus 3CO, that will go to 2Fe plus 3CO2. And then you just add the delta H's. Whoops, I didn't mean to cross that out. You just add them together. So it'd be delta H equals 824.4 plus whatever 3 times negative 282.7 is. And again, there was an example like this on our homework for this weekend that hopefully help reinforce this. But I am now out of time. So if you do have questions before Wednesday, please email me them and I'll be happy to try and answer them as best as I can. I'll put up the equation sheet here in a little bit. I'll put up a homework to cover what we did today. That's not due till Sunday, so you don't need to worry about it until then. Otherwise, good luck, everybody. Hope we all do well. And I shall see you all on Friday. Take care, everyone.